Today in this tutorial, we will discuss about heap sort algorithm. This is the outline of our tutorial. What is heap sort in data structure, when to use heap sort, explanation of heap sort algorithm, example of heap sort, time complexity of heap sort, advantages and disadvantages of heap sort, and application of heap sort. So what is heap sort in data structure? Heap sort is a comparison based sorting algorithm that sorts an elements in ascending or descending order by transforming it into a binary heap data structure. So as we know that all the sorting techniques are used to arrange the element in ascending or descending order. So it uses the concept of max heap and min heap, where the max heap, the largest element is the root, and the min heap, the smallest element is the root node. So if the proper elements are arranged in the max heap or min heap, we can identify the presence of the element in the root element. If the largest element present at the root is a maximum, or we can say that the largest element is present at the root, then we can say that it is a max heap, or if the smallest element present at the root, then we can say that it is the min heap. When to use heap sort? Heap sort is often used when the data size is large and memory is limited. In algorithms, there are different situations will arise whenever we have to analyze the proper sorting algorithm so that we can apply it in the specific problem. So we have to focus on that whenever a very large amount of data are given and the memory is limited, so we have to apply the heap sort to solve that type of problems. Since heap sort is an in-place sorting algorithm, it is more memory efficient as compared to the quick sort and merge sort. Heap sort is also used when stability is important, such as when sorting a list of records based on the multiple fields. Heap sort can also be used as an alternative of quick when the data is already partially sorted or the data has a lot of repeated values. So whenever the elements are given and among these elements a lot of repeated values are present, we can select heap sort as compared to the quick sort. In these cases, quick sort can become very slow due to its worst case time complexity as order of n square. Heap sort, in the other hand, has a worst case time complexity order of n log n, making it more reliable in these cases. So this is heap sort algorithm. So we have to call a function heap sort A indicate the given array. So in step 1, we have to call a function that is called as build max heap. Using this max heap function, we can arrange the element into a max heap tree. Step number 2 consists of 3, 4 and 5. Step number 2 consists of for loop. The variable I will be initialized with length of a and it will continue up to value 2. So in step 3, the value of a of I will exchange with a of 1. In step number 4, the heap size will be decreased by 1, that is heap size a minus 1 will be assigned to heap size a. And in step number 5, we have to call the max heap 5 function so that we can find out the partial sorted elements or the partial max heap tree. So this algorithm will describe about construction of max heap. In step 1, a new node will be created and it will be added at the end of heap. In step 2, we will assign the new value to that particular node. In step 3, we have to compare the value of the child node with its parent. In step 4, if the value of parent is less than the child, then we have to exchange or we have to swap the elements. In step number 5, we have to repeat step 3 and 4 until heap property satisfied. So this is the example of max heap tree. Using these particular elements, we are going to arrange a max heap tree. So the first element is 4. So there is no element present. So this 4 will be treated as the root node or first element. So here in this representation, 4 is defined as the root element. The next element is 3. So now we have to insert this element as a left child of 4. Now we are going to compare the child with the parent. That means the parent value is 4 and the child value is 3. So the condition is true. That means the parent value is greater than the child. So there is no swapping required. So next we will go to the element 7. So 7 will be inserted as the right child of 4. So what happened here? Now we will compare the element 4 and 7. So what we observe that the parent is less than the child. So what we have to do? So we have to exchange the values. So after swapping, we will obtain 7 as the root node, 3 as the left child and 4 as the right child. So now we are going to insert the number 1. So the first label is completed. So now we will insert the 1 as the left child of 3. So what happened? We will compare the parent value and the child. So child value is 1 and the parent value is 3. So parent is greater than child. So no exchange is required. So the next element is 8. Now 8 will be inserted as the right child of 3. So now we are going to compare the parent and the child. So here we observe that the parent value is less and the child value is greater. So now we will apply the swapping or exchange. So after swapping or exchange, the result obtained is 7 as the root, the left child of 7 is 8. So previously 3 was the left child of 7. Now after swapping, 8 is the left child of 7. So what happened? Now we will compare the value 8 with 7. So we observe that whenever we compare the two values, the parent value is less. So we have to apply the swapping or exchange. So after swapping, we obtain that 8 is the root value and the left child of 8 is 7 and the rest values are as it is present. So now we are going to insert 5. So 5 will be inserted as the left child of 4. So now we will compare the parent and the child. So here parent value is 4 and the child value is 5. So we will apply the exchange process. So after swapping, the result is obtained as the root is 8, the left child of root is 7, the right child of 8 is 5. So previously it was 4. Now after swapping, 5 will be the right child of 8. And the left child of 7 is 1, right child of 7 is 3 and the left child of 5 is 4. So this is the max heap, or we can say that this is the final structure of max heap. Using the previous elements, we have arranged the max heap. Now understand max heap construction by an illustrated diagram. Okay, so 35 is the first element. So 35 will be treated as the root element. The next element is 33. So 33 will be inserted as the left child of 35. So now we have to compare 35 with 33. The root element is greater, so there is no exchange required. So now 42 will be inserted as the right child. Here we observe that 42 is greater than root node. So what happened? 42 and 35 will be swapped. So next 10 will be inserted as the left child of 33. So now we will compare 33 is greater, so no exchange is required. Now 14 will be inserted as the right child of 33. So here also no swapping will be required. So now 19 will be inserted. So 19 will be inserted as the left child of 42. So there is no exchange required. Now 27 will also inserted as the right child of 42. So there will no exchange required because root is the higher value. Now 44 will be inserted and it will be inserted as the left child of 10. So you can observe that 44 having the higher value. So it will exchange and it will reach at the root element. Now 26 will be inserted. So 26 will be inserted as the right child of 33. Okay, so there is no exchange required. 31 will be inserted as the left child, and here some swapping will be required because it does not satisfy the condition. So using this property, we can observe that how we can create a max heap from the given set of elements. Okay, so this is the max heap deletion algorithm. Okay, so using this algorithm, we can delete a particular element from the max heap. So in step 1, we have to remove the root node. So the max heap tree is present. In step 1, we have to remove the root node. In step 2, move the last element of last label to root. So what we have to do now? We have to find out the last label, and in last label, the last element will be moved to the root node. In step 3, compare the value of this child node with its parent. That means after swapping, now we have to compare both the childs and we have to compare the child values again with the parent value. In step number 4, if value of parent is less than the child, then we can swap the elements. And in step number 5, we will continue this process, that means step number 3 and step number 4 until heap property holds. So let us understand max-heap deletion. So now here this max-heap tree is given, 44 is the root element and the last element in the last label is 14. So what we have to do? We have to remove as per the algorithm, we have to remove the root node. Here root node is 44. Now we have to remove the 44 and we will insert the element 14 in place of 44. So what happened here? As per the previous instruction, we have deleted the node 44, or we can say that that particular element is already sorted. Now 14 is the new parent of 42 and 35. So what we will do now? We will compare the childs, that is 42 and 35. We observe that in between the two childs, 42 is the higher element. So again we will compare this value with the parent node. Here 14 is less than 42. So what we will do? We will swapping. That means 42 will be the right child and the left child of 42 will be 14. So as in this diagram, we observe that 42 is the root node and 14 is the left child. So what happened? 14 is the new parent of left child 33 and right child 31. But previously 42 was the parent of these two children. So what we have to do now? We have to compare both the children, that means 33 and 31. Here we observe that 33 is greater than 31. So again we have to compare this value with the parent node, that is 14, and we observe that 14 is less than 33. So we have to swap the elements. That means 33 will be the root and 14 will be the left child of 33. So here we observe that 33 now become the root node and 14 is the left child of 33. So now previously 33 was the parent of 10 and 26. After swapping, 14 is the parent of 10 and 26. So what we have to do now? Again we have to compare its two childs, that is 10 and 26, and we found that 26 is greater than 10. So now this 26 will be compared with 14. So we observe that 14 is less than 26. So what we have to do? We have to swap the elements. That means 26 will be the root node and the right child of 26 is 14. So this is the partial sorted elements, or we can say that this is the resultant max tree after deleting the element 44. In this process, we will delete the elements from the max heap. This is the simple example how we can delete a particular element from the max heap. So let's understand max heap deletion by an animated illustration. So now this is the max heap. So what we have to do? We have to exchange the root node with 14. Okay. So now 14 is deleted. Now the two childs are 14 and 35. So now we will compare the values. So after that we observe that from these two different values 42 is greater. So 42 will be the root node and the left child of 42 is 14. So now 14 will compare its two child nodes, that is 33 and 31. We will observe that 33 is the greater one. Now 33 will be the root node and 14 will be considered as the left child of 33. Now 14 will be compared with both the childs. So here we observe that one child that is greater than 14, that is 26. So 26 will be the root and 14 will be treated as the right child of that 26. So that means after deleting or removing the node 44, the max heap having the root node is 42. So again we have to apply the same process with the node 42 and 14, so that we can conclude the whole process, and using this type of deletion process we can remove the root node and we can place this root node as the sorted element. The left side image indicate the max heap tree. Okay. So 8 is the root node, the left child of 8 is 7, the right child of 8 is 5, the left child of 7 is 1, the right child of 7 is 3, and the left child of 5 is 4. So this is the max heap. Now we want to sorting these elements using heap sort algorithm. So what we have to do? We have to delete the root element, that is 8, and after that we will replace the last element of the last level, that is 4. So what we have to do? Now 4 is the root element after swapping, and the left child of 4 is 7 and the right child of 4 is 5. The left child of 7 is 1 and the right child of 7 is 3. Now that 8 that we removed from the root node, we can say that it is already sorted. So now what we have to do? We have to compare the children of root node 4, that is 7 and 5, and we observe that 7 is greater than 5, so that we will compare the 4 and 7. So after comparison, we obtain that the parent value 4 is less. So what we have to do? We have to swapping now. So 7 will be the root node and the left child of 7 is 4. Now what happened? Previously the root node was 7 for child 1 and 3. Now after swapping, the root node is 4. So what we have to do? We have to check with its parent children's. Now the root node having the higher value, so there is no further exchange or swapping is required. So this is the tree after deleting of the node 8. So now we will exchange 7 and 3. So here 7 and 3 will be exchanged, 3 will be the root node, and we can say that the element 7 that is removed from the root node is already sorted. Okay. So previously the root node was 7, that means 7 was the parent for 4 and 5. After swapping, now 3 is the parent for 4 and 5. So now we will compare the childs, that is 4, 5, we have to compare. So after comparison, we obtain that 5 is the greater element. So now we will compare this 5 with the root node 3. We observe that 3 is the smaller than 5, so we will exchange. So after exchange, 5 will be the root node, the left child of 5 is 4 and the right child of 5 is 3 and the left child of 4 is 1. So now we will exchange 5 and 1. So after exchange, 1 will be the root node, and we can say that the 5, the element we have removed from the root node, is already sorted. So after that, now the left child of 1 is 4 and the right child of 1 is 3. So what we have to do now? We will compare both 4 and 3. So after comparison, we obtained 4 is the greater element. So now we will compare this 4 with the root node 1. We observe that the root node is less than the child node. So what we have to do? Now we have to swap or exchange the values. So after swapping, 4 will be the root node, the left child of 4 will be 1 and the right child of 4 will be 3. So now you have to find out that the last label and the last element is 3. So we have to exchange 3 and 4, and after that the root element will be 3 and the left child of this 3 will be 1, and we have removed this 4 from the root node. So we can observe that, or we can conclude that this the element 4 is already sorted. So now there are 2 remaining elements are present, that is root node is 3 and the left child of root node is 1. So now we will compare the elements. So definitely here the root node is 3. So we have to just swapping the elements. Now the root node will be the 1 and we will remove the root node, that is 3, and we can say that the 3 is already sorted. So now there is a single element present. Now we can remove the element and we conclude that this particular one is also sorted. So after processing all the steps, the final output is 1, 3, 4, 5, 7 and 8. So using this heap sort algorithm, we arrange the element in ascending order. So we can use this process, that means first we will construct a max heap, then after using the deletion algorithm, we can find out what are the sorting sequence of the given elements. Now come to the time complexity of heap sort. So as we know that the whole heap sort is divided in 2 parts. One is for building a max heap and second one is called the heap5 function. Okay. So time complexity for building a max heap is defined as order of n, and the time complexity for each instance of heap phi is defined as order of log n. So as we know that heap sort is the combination of building a max heap and apply the heap phi. So if we combine both these functions, then the overall time complexity of heap sort in best case, worst case and average case will be defined as order of n log n. Here n is the time complexity to create a max heap and log n is the time complexity to define the heap phi. So now advantages of heap sort. So first advantage is efficient. So heap sort has a time complexity of order of n log n, making it one of the most efficient sorting algorithms, because we know that the merge sort and quick sort best case time complexity is also order of log n. Merge sort having the time complexity of order of n log n in all the three cases, best case, worst case and average case. But quick sort having the time complexity of order of n log n in best case and average case, but the worst case time complexity of quick sort is order of n square. So in the form of efficiency, we can conclude that heap sort has a better efficiency having order of n log n as compared to the other sorting algorithms. In-place sorting. Heap sort is an in-place sorting algorithm, which means it sorts the elements within the input array without using any extra memory. This makes it more memory efficient than other sorting algorithms like quick sort and merge sort. Next advantage is stable sorting. So heap sort is a stable sorting algorithm, which means that the relative order of elements with equal values is preserved. This is more important in many applications where the elements are records with multiple fields and the sorting is based on multiple criteria. So whenever we will face this type of situation, that means we will prefer the stable sorting algorithm. So to solve this type of problem, wherever some parameters are given like this, we will use heap sort as compared to the other sorting algorithms, because it is one of the stable sorting algorithm. Easy to implement. So heap sort is easy to implement and understand, making it a good choice for students and beginners who are learning data structures and algorithm. Because whenever we are in the beginning phase, we must have to select an algorithm which can be easily implemented. So in case of heap sort, we have to concentrate on the two things. First is that we have to create a max heap. This is the easy process. We know how we can create a max heap from the given set of elements. And the second is heap phi. That means how we can delete the elements after creating the max heap. That means we can easily implement this heap sort. So we can conclude that whenever we are at the beginning stage, that means we are going to design some algorithm or sorting algorithms. So as a student point of view, we can implement the heap sorting algorithm, because it is easy to implement and easily we can understand the things that present in the heap sort. So as a student point of view, we must pick the heap sort whenever we are in the beginning stage. Now we will discuss about the disadvantage of heap sorts. So the first disadvantage is not the fastest one. So although heap sort is efficient, it is not the fastest algorithm, because quick sort and merge sort are generally faster as compared to the heap sort in practice. Okay. So the disadvantage is that it is not fastest algorithm, because there are two different fastest algorithms are present. They are quick sort and merge sort. So in case of faster, there is some disadvantage present in the heap sort. Second is not adaptive. Heap sort is not adaptive, which means it does not perform well on partially sorted array or arrays with many repeated values. In these cases, quick sort is better choice. So whenever a problem is given and in that particular problem maximum number of repeated values are present, so in that case we will prefer quick sort as compared to the heap sort, because heap sort is not so adaptive. So when the partially sorted elements are given, suppose some elements are given, 10 or 12 elements are given, in that 50% elements are already sorted sequence. That means some elements are partially sorted. In that case also we can't use heap sort, because to perform in this type of scenario, quick sort will be the preferable choice. So we have to concentrate that whenever a problem is given, when more number of elements are already partially sorted or elements are present having repeated values. In that case, it is not adaptive. That means user can pick quick sort as compared to the heap sort. So these are the two basic disadvantages of heap sort. Now application of heap sort. So where we can apply the heap sort, because it is very much important to not only to analyze the algorithm, but we have to learn where we can apply the sorting techniques. Okay. So if there are different scenario will be given, different problem statement will be given. So we have to analyze that this particular problem, which algorithm will be suitable or which algorithm we can apply to solve this particular problem. So application plays a vital role in every sorting. So now we will focus on what are the different areas where we can apply the heap sort. First one is sorting large data sets. Heap sort is a good choice for sorting large data sets due to its time complexity of order of n log n and its ability to sort elements in place. So these are the two primary factors. Using these primary points, we can apply the heap sort. This make it deal for the applications where memory is limited, such as embedded system or mobile devices. Because we have already mentioned that whenever a huge data set is given with a less memory, in that particular time we can apply the heap sort. So in embedded system and mobile devices where memory are very less, we can pick the heap sort for its application. Priority queues. Heap sort is used in the implementation of priority queues, which are data structures that store elements with priorities and allow efficient access to the element with the highest priority. So whenever we are going to design the priority queue, in that cases we can apply the heap sort algorithm. Next one is graph algorithms. Heap sort is used in graph algorithms such as Dijkstra shortest path algorithm to efficiently find the shortest path between two nodes in a graph. So these are some points where we can apply the heap sort algorithm, where the memory is less, where the data is maximum, or where we are going to design the priority queue or graph algorithms. In these cases, we can apply the heap sort algorithm. So here is the conclusion. So what we observe from this description is that heap sort is a sorting algorithm that is based on the binary heap data structure. It has a time complexity of order of n log n and is considered as a stable sorting algorithm, meaning that the relative order of equal elements is preserved in the sorted output. Heap sort is widely used due to its versatility, performance and low memory requirements. So this is all about heap sort. So you must have to go through the algorithms, how we can construct a max heap, how we can apply the heap file to sorting the elements, and the important point is that where we can apply the heap sort to solve a particular problem. Thank you very much.